Hello, my name is Kai. I'm so honored to share work here at NAACL titled Towards Lifelong Dialogue Agents via Timeline-Based Memory Management. As we know, throughout a dialogue agent server's life, it should constantly keep track of information, experiences, and events shared with users and converse accordingly. To support this, most systems adopt a summarize then retrieve paradigm, where past conversations are summarized into memories and later retrieved to augment response generation. Here, memory updating is often used to avoid a memory pool overloaded with outdated memories, which can hinder retrieval accuracy and response quality. However, we find such updating often leads to information loss. Let's take a look at this example. In dialog session 2, we collect a memory. A is afraid of ships due to not being able to swim. Later, in session 4, A expressed interest in swimming. Therefore, the memory updating mechanism deleted the previous memory from the timeline. However, now a new user input says that A used to be afraid of anything related to water. But since the earlier memory was deleted, the agent fails to retrieve this information and therefore generates an improper, contradictory response. You might be wondering, if memory updating causes information loss, why not just feed the whole dialog history to the agent? Well, although this is feasible with recent LLMs having large context windows, it often biases agents towards the latest user input. At this point, we identify two core challenges for lifelong dialogue agents. First, during memory construction, how do we store large-scale past interactions effectively without removing old memories? Second, during RG, how do we collect relevant contextual cues from an ever-growing memory span? In this work, we address these challenges separately yet complementarily. We discard memory updates to avoid information loss and preserve relevant memories in the linked timeline. And we retrieve the memory timeline as a whole rather than isolated memories. We hereby present a novel framework called thinning. It consists of three main phases: memory graph construction, timeline retrieval and refinement, and timeline augmented RG. Now let's dive into the process of our framework. At the end of a dialogue session, the conversation is summarized into several new memories, each linked to the memory graph. Inspired by how humans make connections between relevant events, we implement relation-aware memory linking. Here, we first identify existing memories that have strong common sense causal relations R with the new memory using embedding similarity and an LLM's reasoning. These associated memories are marked yellow in figure A. Then we look at each connected component containing at least one associated memory. And we trace through the future direction, finding the most recent associated memory and linking the new memory to it. Now, we've linked new memories to the memory graph. We are ready to start a new dialogue session. Using a new conversation as query, we retrieve the relevant memory timelines and prepare them for later RG. We start by identifying top K relevant memories using a retriever and locating the connected component to which they belong, similar to what we did previously. After that, we take the oldest memory in each component as the starting point, trace through the future direction, and untangle the component into several raw memory timelines. So we've collected a raw memory timeline. Now, although we can directly use this timeline to augment RG, we choose to implement a refinement process to tailor the timeline to the current dialogue in order to address the discrepancy between offline memory construction and real-time conversation. Finally, the agent uses the refined timeline to generate the next response. Now, using two datasets of multi-session conversations, we evaluate our framework via both common procedures and our design pipeline, which will be introduced later. Starting from response quality, thinning outperforms both conventional and LLM-based recent baselines in long-term conversations. Also, we observed that memory updates led to worse performance compared to simple memory retrieval. This observation justifies our effort to develop an update-free approach. Next, the ablation study shows that whilst all phases contributed to performance gain, addressing common sense relation between memories contributed the most. Moreover, we conducted an experiment where the retrieve timeline was broken down into separate memories and their order was shuffled. We found this setting outperforms conventional retrieval, indicating that timeline retrieval is better at capturing relevant memories. Following these findings, we further showed that our framework can retrieve memories that are more helpful than baselines in both G-eval and human evaluation. In addition to helpfulness, we manually labeled the golden memory for each test data and showed that our framework has higher retrieval accuracy. As a result, our agent demonstrates a higher percentage of responses in telling and not contradicting past conversations. Okay, so as you can see, so far we've utilized extensive human evaluation to assess our agents. The reason is that the golden mapping between the current dialogue context and reference memory is often unavailable, and G-eval can be limited by the ability of the evaluator LLMs. So we propose T-form, a human-free evaluation pipeline using counterfactual questions to test agents' ability to refer to the past. These counterfactual questions are designed to trick dialogue agents into believing a non-existent event. For instance, when the agent is representing a person who's never been to Japan, we deliberately ask, "Hey, did you have a great time in Tokyo?" Applying this pipeline, we showed that our agent yielded a higher success rate of not being fooled by the questions, proving its ability to recall the past. At this point, you might have this question in mind. Okay, the agent looks promising. However, isn't it simply because timeline retrieval provides more memories using its linked structure? So we first confirmed that, on average, we retrieve fewer memories than the baselines. However, in later dialogue sessions, our retrieved timeline sometimes contains more memories than the best performing baseline memory retrieval. Therefore, we address this question by manually equalizing the number of retrieved memories across baselines to match our agent's retrieval count, and the results still hold true in this scenario. Lastly, a remaining question is whether the multiphasic nature of thinning leads to more computational costs. We answer this question by plotting API costs against response quality. We found that thinning and its ablation sit on the Pareto frontier, indicating an efficient cost-performance trade-off. The same also holds for thinning's trade-off between time and performance. Okay, so let me wrap things up by going through the takeaway of this presentation. Represents thinning, a timeline-based memory management framework for lifelong dialogue agents. Although the concept of time has been adopted in prior work, we are the first to model event timelines in memory management and response generation. We showed that this timeline-based approach can facilitate more effective lifelong memory tracking and integration into response generation. Here are two remaining issues we plan to explore in future work, and these are the reference papers. Thank you so much for listening to my presentation. I hope you all have a great time here in Albuquerque.